There is a comforting rhythm to the passage of time here on Earth. It is the beat of a resting heart, the steady rise and fall of the tides, and the mechanical precision of the second hand sweeping around the face of a clock. We live our lives governed by this invisible metronome, trusting implicitly that a second is a second, a minute is a minute, and an hour is an hour, regardless of who is watching or where they might be standing. It feels absolute, a rigid scaffolding upon which the universe is built. We imagine time as a great silent river that flows at a constant, unyielding pace, carrying everything from the smallest atom to the largest galaxy along with it, never speeding up, never slowing down, and never pausing for breath. This perception of universal time is perhaps the most convincing illusion the human mind has ever constructed. It is an intuition born of our limitations, a consequence of living our entire lives on the surface of a single, relatively slow-moving planet, circling a modest star in a quiet corner of the galaxy. In our daily experience, we never move fast enough, nor do we stand near anything massive enough to shatter this illusion. We simply do not see the seams in the fabric of reality. But if we could step outside our terrestrial bubble, if we could travel at speeds that rival the flight of a photon, or stand upon the precipice of a neutron star, we would see that the river of time is not steady at all. It is turbulent. It meanders. It stretches and compresses, flowing rapidly in the shallow voids of empty space and pooling into sluggish, frozen eddies near the giants of the cosmos. To understand why a human being might age slower in the depths of space than in the comfort of their living room, we must first dismantle this deep-seated belief in a universal clock. We must accept a truth that seems to defy all common sense. That time is not a fixed backdrop against which events play out, but rather a dynamic, malleable participant in the drama of the universe. It is personal. It is subjective. It belongs to the observer, and no two observers ever truly share the exact same experience of now. The unraveling of absolute time begins with light. When we look up at the night sky, we are not seeing the universe as it is at this very moment. We are seeing a ghost. The light from the moon takes just over 1 second to cross the gap between the lunar surface and our retinas. The light from the sun is 8 minutes old by the time it warms our skin. When we gaze at the nearest stars, we are looking years into the past, and when we peer at the faint, smudge-like glow of a distant galaxy, we are witnessing events that transpired millions of years ago, long before our species walked the earth. We accept this delay as a consequence of distance. We understand that light, despite being the fastest thing in existence, still requires time to travel. However, there is a deeper secret hidden within the speed of light, one that changes everything. For centuries, physicists believed that speed was additive. If you were standing on a train moving at 60 kilometers per hour and you threw a ball forward at 20 kilometers per hour, a person standing on the platform would see that ball moving at 80 kilometers per hour. It makes perfect, intuitive sense. But light refuses to obey this rule. Imagine you are drifting through the darkness of space in a futuristic vessel, traveling at half the speed of light. You turn on a headlight beam that shoots out into the void ahead of you. To you, that beam races away at the speed of light. Now, imagine a stationary observer watching your ship fly past. Common sense suggests that they should see the beam traveling at 1.5 times the speed of light, your speed plus the beam's speed. But they do not. They see the beam traveling at exactly the speed of light, no faster, no slower. This sounds impossible. How can two different people moving at vastly different speeds measure the same beam of light traveling at the exact same velocity? It seems to break the laws of mathematics. But the universe does not care about our mathematics or our intuition. It cares about the speed of limit. If the speed of light is immutable, a cosmic constant that cannot be broken, then something else has to give way to make the numbers balance. That something else is space and time. For the speed of light to remain constant for everyone, the very definition of a second and a meter must change depending on how fast you are moving. This was the revelation that rewrote our understanding of reality. It implies that time is not separate from space, but woven together with it into a single, four-dimensional fabric known as space-time. When you move through space, you are essentially trading your motion through time. Think of it like a car driving across a vast, flat salt flat. If the car drives strictly north, all its progress is dedicated to the northward direction. If it turns and drives northeast, it is still moving at the same speed. But now some of its motion is being used to travel east, so its progress north slows down. We are all traveling through space-time at a constant speed, the speed of light. When we are sitting still in a chair, all of that motion is directed through time. We are hurtling towards the future at maximum velocity. But the moment we stand up and walk, or climb into a rocket and blast off, we divert some of that motion through space. By moving through space, we necessarily slow down our motion through time. This is the essence of why we age slower in space, or more accurately, why we age slower when we move. It is not that the biological processes of the body magically decide to pump the brakes. The heart does not choose to beat slower. The cells do not decide to divide less frequently. To the astronaut traveling at high speed, everything feels completely normal. Their watch ticks at the same rate it always has. They speak and think at their usual tempo. If they were to check their pulse, it would be 70 beats per minute, just like on Earth. The difference only becomes apparent when they compare their clock with a clock that was left behind. It is a difference of perspective, but it is a difference with physical consequences. The astronaut has taken a different path through space-time. They have traveled a route that spans more distance in space, and, as a mathematical necessity, spans less distance in time. They have literally experienced fewer seconds than the person who stayed home. This shattering of the universal now has profound implications. It means that simultaneity is an illusion. Two events that appear to happen at the exact same instant for one person might happen hours, years, or even centuries apart for another, depending on their relative speeds and positions. Imagine a supernova exploding in a distant galaxy. For an astronomer on Earth, the explosion happens today. For an alien traveler moving towards Earth at near-light speed, that explosion might have happened weeks ago. For another traveler moving away from Earth, the explosion has not happened yet. It lies in their future. There is no single master clock ticking in the center of the universe, keeping everything synchronized. Every single particle of matter, every planet, every star, and every wandering astronaut carries their own personal measure of time. We are each trapped in our own temporal bubble, and while these bubbles usually align closely enough for us to agree on a meeting time for coffee, they are never perfectly in sync. When we consider the vast distances of space, this disconnect becomes the defining feature of reality. The reason we feel time is shared is simply that we are huddled so close together on this one rock, moving in roughly the same direction at roughly the same speed. We are like a choir singing in unison, unaware that if we were to scatter to the winds, our harmonies would drift apart until we were all singing entirely different songs. This realization forces us to reconsider what it means to age. Aging is fundamentally a physical and chemical process. It is the accumulation of molecular damage, the shortening of telomeres, the gradual wearing down of the machinery of life. All of these processes require time to happen. They are sequences of events. A protein folds, a cell divides, a neuron fires. These events occur in a linear order, one after the other. If time itself, the medium in which these events occur, is stretched or compressed, then the rate of aging must follow suit. It is important to visualize this not as the clock slowing down, but as the path getting longer. Imagine two hikers setting off for the same mountain peak. One hiker takes a straight, direct path up the gentle slope. The other hiker takes a winding, jagged route that traverses the entire width of the valley before reaching the top. They both arrive at the summit, but one has walked 5 kilometers while the other has walked 50. In the landscape of space-time, the distance walked is measured in seconds and years. The person who stays on Earth takes the straight path through time. The astronaut who rockets into the cosmos takes the winding path. When they meet again, they have traversed different lengths of existence. The astronaut has literally walked fewer miles in the dimension of time. This phenomenon is often discussed in the abstract, a quirk of mathematics to be debated in lecture halls. But it is not abstract. It is as real as gravity or electromagnetism. It is happening right now, even at the minuscule scales of our daily lives. Your feet, being closer to the center of the Earth, are aging slightly slower than your head. A commuter driving on the highway is aging nanoseconds slower than their spouse waiting at home. These differences are too small for our biology to notice, vanishing into the noise of existence, but they are there. As we cast our minds outward to the prospect of interstellar travel, these microscopic differences billow out into vast chasms. The illusion of universal time is the first casualty of leaving our home planet. To become a spacefaring species is to accept that we will no longer share the same history or the same future. A father might leave on a voyage and return younger than his daughter. A twin might say goodbye to their sibling and reunite as a generation apart. The structure of the universe is built on this flexibility. It allows for a kind of preservation that seems magical to our earthbound sensibilities. Speed is a preservative. It is a form of suspended animation that requires no ice and no sleeping pods, only the raw application of velocity. By moving faster, we cling tighter to the present moment, dragging it out, refusing to let it slip into the past. But why does the universe work this way? Why is there this trade-off between motion in space and motion in time? It suggests that there is a fundamental limit to how much happening can occur in the universe. There is a capped budget of existence for every object. You can spend that budget sitting still and letting the years wash over you, or you can spend it racing across the stars, keeping the years at bay. You cannot do both. This leads us to a strange and beautiful thought, that light, which moves at the maximum possible speed through space, does not experience time at all. From the perspective of a photon, the journey from the surface of a star to the eye of an observer, a journey that might take 1 billion years from our perspective, happens instantly. For light, emission, and absorption are the same moment. Time is a property of mass, a burden borne by things that are heavy and slow. To be made of matter is to be stuck in time, to be forced to age, to be subject to the slow decay of entropy. To be light is to be timeless. As we humans build our ships and ignite our engines, we are trying to shed some of that burden. We are trying to become a little more like light. We push our massive, fragile bodies faster and faster, fighting against the anchor of our own existence, trying to steal a few more moments from the grip of eternity. And the universe, in its indifferent consistency, grants us this wish. It slows our clocks, it preserves our cells, it holds our aging at bay, provided we are willing to leave everything we know behind. The dismantling of universal time is a disorienting concept. It leaves us floating without an anchor, drifting in a sea where when is just as relative as where, but it is also a liberating truth. It reveals a cosmos that is far more intricate and interconnected than the rigid clockwork universe of our ancestors. It shows us that we are not merely inhabitants of a static stage, but participants in a fluid, dynamic dance of space-time. So, when we ask why we age slower in space, we are really asking about the nature of reality itself. We are asking how the simple act of moving can alter the fundamental flow of cause and effect. The answer lies not in biology, but in geometry. It lies in the strange, curved, and flexible architecture of the universe, where the faster you run, the slower the world turns. This is the foundation upon which we will build our understanding. We have stepped off the platform of Earth and realized that the train of time does not move at the same speed for everyone. Now that we have broken the illusion of the universal clock, we are ready to explore the specific mechanisms that allow this time travel to occur. We are ready to look at what happens when we push the speedometer towards the ultimate limit, and how the sheer velocity of our travel acts as a shield against the ravaging effects of the years. We turn our attention next to the velocity of youth and the strange preservation of the high-speed traveler. To understand the preservation of youth in the vastness of the cosmos, we must turn our attention to the nature of speed itself. In our daily lives, speed is a matter of convenience. It is the difference between a long commute and a short one, or the thrill of a racing car tearing down a track. We measure it in minutes saved or in the adrenaline of the moment. But in the deep architecture of the universe, speed is something far more profound. It is a protective barrier. It is a shield against the relentless march of entropy. When we speak of the velocity of youth, we are describing the physical reality that the faster an object moves through space, the slower it moves through time. This concept feels inherently wrong to our biological instincts. If you run faster, your heart beats harder, your breath comes quicker, and you feel as though you are living more life in every second, not less. But the universe operates on a logic that exists far beyond the limitations of human biology. To grasp it, we must imagine time not as a flowing river, but as a thick, viscous substance like honey. When you are standing still or moving slowly, the honey flows past you with ease. But as you pick up speed, as you push against the fabric of space with greater and greater force, the honey thickens, it resists. The faster you push, the harder it becomes to move through time, until the seconds themselves begin to drag and elongate. This is the phenomenon known as time dilation, a cornerstone of special relativity. It dictates that time is elastic. It stretches when under the tension of extreme velocity. However, this effect does not reveal itself at the modest speeds we travel on Earth. When you fly in a commercial jet at 900 kilometers per hour, you are technically aging slower than the people on the ground below you. But the difference is so infinitesimally small, measurable only in nanoseconds, that it vanishes into the noise of existence. To truly see the velocity of youth in action, to see speed act as a true preservative, we must approach the ultimate limit of the cosmos, the speed of light. Light travels at approximately 300,000 kilometers per second. It is a number so large, it creates a disconnect in the human imagination. At this speed, you could circle the Earth 7 times in the span of a single heartbeat. It is the speed limit of the universe, the maximum velocity at which cause can lead to effect. Nothing with mass can ever truly reach it, for as you approach this limit, the energy required to push you faster climbs toward infinity. But we can get close. And it is in this approach, in the near light speeds, that the magic of time dilation begins to unfold. Imagine a spacecraft designed to travel at 99% of the speed of light. This is a vessel built to cheat death, a machine that trades space for time. Inside this ship, life proceeds exactly as normal. The hum of the ventilation fans, the brewing of coffee, the conversation between crew members, all of it happens at a standard rhythm. If you were a passenger on board, you would not feel heavy, nor would you see your movements slowing down in a mirror. You would simply be living your life. But if you were to look out of a window, back toward the world you left behind, you would witness a reality that defies belief. From your perspective, the universe outside would seem to be fast-forwarding. The galaxy would rotate with frantic energy. Stars would be born, live their billions of years, and die in explosions of light, all within what feels like a mere season of your life. By traveling at such extreme velocities, you have effectively disengaged from the timeline of the rest of the universe. You are skimming across the surface of time, like a stone skipping over water, touching down only fleetingly, while the depths of the ocean remain undisturbed below you. To understand why this happens without relying on complex mathematics, we can use a simple visual analogy involving a clock made of light. Picture a clock that consists of 2 perfect mirrors, one placed on the floor and one on the ceiling, facing each other. A single photon of light bounces up and down between these mirrors. Tick, tock, tick, tock. Each time the photon hits a mirror, 1 second passes. Now, imagine this clock is sitting on a train platform. The photon travels in a straight vertical line, up and down. The path is short and direct. But now, place this clock on a train speeding past the platform at an immense velocity. From the perspective of someone standing on the platform, watching the train rush by, the photon does not just go up and down. Because the mirrors are moving sideways with the train, the photon has to travel diagonally to catch up with the top mirror, and then diagonally again to hit the bottom mirror. The diagonal path is longer than the straight vertical path. We know from geometry that the hypotenuse of a triangle is longer than its vertical side. This is the crucial realization. The photon on the moving train has to travel a farther distance to complete a single tick of the clock. Here is where the laws of the universe intervene. Since the speed of light is constant and cannot speed up to cover this extra distance, it simply takes longer for the photon to make the journey. The tick takes longer to happen. Therefore, time itself on the moving train must be running slower relative to the platform. The faster the train moves, the more stretched out that diagonal path becomes, and the longer each second takes to pass. This is not a mechanical failure of the clock. It is a fundamental property of existence. Every atom in the astronaut's body is essentially a tiny clock, governed by the interactions of forces moving at the speed of light. The electrons orbiting the nucleus, the chemical reactions firing in the brain, the division of cells, all of these are dependent on the exchange of energy and particles. When the body is moving at extreme speeds, these internal interactions have to cover more distance through space to complete their cycles. The entire biological machinery slows down relative to a stationary observer. We see proof of this not in starships, which we have yet to build, but in the rain of subatomic particles that showers the Earth every day. High in the upper atmosphere, cosmic rays from deep space collide with air molecules, creating short-lived particles called muons. These muons are unstable. They are born with a desperate, frantic lifespan, destined to decay and vanish in roughly 2/millionths of a second. Even traveling near the speed of light, 2/millionths of a second is not enough time for them to reach the surface of the Earth. By all accounts of Newtonian physics, they should disintegrate high in the clouds, never to be seen by detectors on the ground. And yet, we detect them constantly. They pass through our bodies and our buildings, reaching the surface in vast numbers. For decades, this was a mystery. How could something survive a journey that is longer than its own lifespan? The answer is the velocity of youth. Because the muons are hurtling toward the ground at nearly the speed of light, their internal clocks have slowed down dramatically from our perspective. What feels like 2/millionths of a second to the muon might be 10 or 20 times that duration to us. Their extreme speed preserves them, stretching their brief flash of existence just long enough to complete the journey. They are travelers from the upper atmosphere who have aged slower than the air they pass through. This preservation effect grows exponentially the closer you get to the speed of light. At 50% of light speed, the time dilation is noticeable but modest. You might age 87 minutes for every 100 minutes that pass on Earth. At 90%, the effect is profound. You age 44 minutes for every 100. But as you inch closer to the decimal points, 99.9%, the curve skyrockets. You could travel to the center of the Milky Way, a journey of 25,000 light years, and arrive in what feels like just a few decades of personal time. You would emerge from your ship still young, perhaps having aged only 20 years, while outside, civilizations have risen and fallen, and the star you aimed for might have long since evolved into a red giant. There is a melancholic beauty to this reality. It suggests that exploration of the deep universe is a one-way door in time. The faster we go, the more we separate ourselves from the people we love. To be a traveler of the stars is to be an exile of time. You cannot have both the speed to reach the edge of the galaxy and the ability to return to the home you knew. The velocity that grants you youth also demands that you leave your era behind. This leads us to reconsider the human obsession with longevity. We search for biological cures for aging, for diets and medicines that will grant us a few more years. But the laws of physics offer a different solution, one that is mechanical rather than biological. Preservation is a matter of location and velocity. If you could move fast enough, you could outlive the sun. You could watch the slow dance of the galaxies as they merge and drift apart, witnessing the cosmic history of billions of years unfolding in the span of a human lifetime. However, we must also acknowledge the energy cost of such a state. The universe does not give away this time for free. As an object approaches the speed of light, it gains mass. The heavier it gets, the more energy is needed to push it faster. To reach the speeds where time dilation becomes truly dramatic, a spacecraft would need to consume energy equivalent to the output of entire stars. The universe seems to hoard its moments of frozen time, locking them behind a wall of energy that is incredibly difficult to scale. We are, for the moment, trapped in the slow lane, aging at the standard rate of 1 second per second, purely because we lack the power to break free. But the principle remains. The connection between motion and time is unbreakable. Every time you walk down the street, you are technically exploiting this rule, however negligibly. The geometry of space-time curves around your motion, adjusting the flow of seconds to match your speed. It is a comforting thought that the universe is responsive to us. We are not just moving through a static stage. We are dragging the scenery with us, warping the duration of our own existence with every step we take. As we look toward a future where propulsion systems might improve, where we might harness the power of fusion or antimatter to propel our vessels to significant fractions of the speed of light, we are looking at the birth of a new kind of human. These travelers will be chrononauts in the truest sense. They will not be jumping back to the past, but they will be sliding into the future at a different rate than the rest of their species. A crew that sets out for a nearby star system might return after a 10-year mission to find that 50 years have passed on Earth. They will be walking anachronisms, young men and women full of vitality, greeting their own grandchildren as peers. The velocity of youth is, therefore, a kind of suspended animation that requires no ice, no sleep, and no chemical stasis. It requires only the raw, silent power of momentum. It is the closest we can come to immortality in a physical sense, to simply outrun the clock. By moving, we are engaging in a cosmic negotiation, trading our position in space for our position in time, balancing the two accounts of our existence. Yet speed is not the only way to bend the curve of time. We often think of space as a void, a place of emptiness, where only velocity matters, but space is also textured. It is filled with the deep, heavy gravity wells of planets, stars, and dark remnants of stellar death. Just as extreme speed can act as a brake on the aging process, so too can the sheer presence of matter. Gravity is not just a force that pulls us down to the ground. It is a force that pulls on time itself, anchoring it, slowing it, and creating pockets of reality where the clock ticks at a different rhythm entirely. We have explored how the race across the cosmos preserves the traveler. Now we must turn our gaze downward, into the depths of the gravity wells, to understand how the heavy hand of the universe grips the second hand of the clock and refuses to let it move. We leave the rushing silence of the void and descend toward the massive giants of the sky. We have explored how the sheer swiftness of travel can act as a preservative, keeping the years at bay through the mechanism of velocity. But there is another force at play in the cosmos, one that is far more pervasive and familiar to us, yet equally capable of bending the rigid hands of the clock. It is the force that holds our feet to the ground, the force that keeps the moon in its orbit, and the force that binds the galaxies together in the dark. It is gravity. When we think of gravity, we typically think of it as a tether. It is the heavy hand that pulls the apple from the tree, or the invisible chain that keeps us from floating off into the void. We experience it as weight, as a burden to be carried. But in the deep geometry of the universe, gravity is not merely a force that pulls on objects. It is a force that pulls on time itself. Just as extreme speed can slow the passage of seconds, so too can the presence of extreme mass. The heavier the object you are standing on, the slower time flows around you. This realization requires us to look at the universe not as a collection of objects suspended in emptiness, but as a fabric. Imagine a vast, taut sheet of rubber stretching out in all directions. If you place a heavy bowling ball in the center of that sheet, it sinks. It creates a depression, a curve in the fabric. Any marble rolling past will follow that curve, spiraling inward, not because it is being pulled by a magnet, but simply because the shape of the surface has changed. This is the vision of the universe given to us by general relativity. Massive objects like stars and planets sit in the fabric of space-time, and their immense weight causes that fabric to sag and warp. But here is the crucial detail that defies intuition. They do not just warp space, they warp time. The depression caused by a massive object is a gravity well, and deep inside that well, time runs thicker and slower than it does on the flat, undisturbed plains of empty space. To understand this, we must imagine time as a density. Out in the voids between galaxies, where there is very little mass to disturb the peace, time is thin and fast. It flows with zero resistance. But as you approach a planet like Earth, the density of the planet drags on the fabric of reality. The closer you get to the surface, the thicker the medium of time becomes. It is as if the seconds are struggling to tick, wading through molasses. This means that gravity is a time machine, albeit a very specific kind. It does not transport you to the past or the future, but it alters the rate at which you reach tomorrow. A person living on the ground floor of a skyscraper is technically closer to the massive center of the Earth than a person living in the penthouse 100 floors up, because they are deeper in the gravity well. The person on the ground floor is aging slower. Their clock ticks with a barely perceptible hesitation compared to the clock in the clouds. This sounds like science, fiction, or perhaps a philosophical riddle with no bearing on reality, but it is a measurable physical fact. The core of our Earth, compressed under thousands of kilometers of rock and iron, is approximately 2.5 years younger than the surface of the planet. It has existed for the exact same duration of history, formed from the same swirling dust cloud at the dawn of the solar system. Yet because it sits in the deepest part of the gravitational well, it has experienced fewer seconds than the mountains and the oceans above it. This phenomenon is known as gravitational time dilation. It dictates that to be heavy is to be slow. We do not notice it in our daily lives because the Earth, for all its grandeur, is a relatively modest rock. Its gravity is strong enough to keep an atmosphere in place, but weak enough that its effect on time is measured in nanoseconds. However, we have built machines that must navigate this reality every single day. Consider the satellites of the global positioning system that circle our planet. These mechanical sentinels orbit roughly 20,000 kilometers above the surface. At that height, the Earth's gravity is significantly weaker than it is here on the ground. The grip of the planet's mass has loosened. Because they are floating higher in the gravity well, where the space-time fabric is less stretched, time for these satellites actually runs faster than it does for us. They are aging more quickly than the cars and smartphones they guide on the ground. If engineers ignored this effect, if they assumed that time was universal and that a clock in space ticked at the same rate as a clock in London or New York, the entire system would fail within minutes. The navigation errors would accumulate, drifting by kilometers every single day. The fact that your phone can pinpoint your location on a street corner is a daily confirmation that time is fluid and that gravity is altering the flow of reality overhead. The relationship between gravity and time becomes even more profound when we look beyond our own solar system to the true giants of the universe. Consider the Sun. It is a mass so great that it accounts for more than 99% of all the matter in our solar system. If you could withstand the heat and stand on the surface of the Sun, you would be standing in a gravity well far deeper than Earth's. There, the drag on time is much more pronounced. A clock on the Sun loses about 1 minute per year compared to a clock on Earth. It is a small difference in the grand scheme of a human life, but over the billions of years that the Sun has burned, it amounts to thousands of years of difference. The face of our star is younger than the space that surrounds it, but even the Sun is a gentle giant compared to the remnants of dead stars. When a massive star exhausts its fuel and collapses under its own weight, it can compress into a neutron star. Imagine a sphere with the mass of 500,000 Earths crushed down into a size no wider than a modern city. The gravity on the surface of such an object is unimaginable, billions of times stronger than what we feel right now. If you were to descend toward a neutron star, you would be entering a region where the warping of time is no longer a subtle curiosity, but a dominant force of nature. Standing on the surface, looking out at the universe, you would see the cosmos accelerating. The external universe would appear to be moving in fast forward, galaxies spinning and stars dying at a frantic pace, while you remained preserved in a bubble of sluggish, heavy time. For every few years that passed for you on that crushing surface, a decade might pass for an observer watching safely from a distance. This brings us to a poetic realization about the nature of down. We tend to think of falling as a movement through space, a descent from a high place to a low place. But in the language of relativity, falling is also a movement through time. To fall is to move toward a place where time runs slower. The apple falls from the tree not just because the earth pulls it, but because the earth offers a path of least resistance through space-time. The apple seeks the place where time is slowest, and that place is the ground. Gravity, then, is the universe's way of braking. It is an anchor. Without gravity, time would race by at its maximum possible speed everywhere, but matter slows it down. Matter clumps together, forming stars and planets, and in doing so, it creates pockets of slow time in the rushing river of the cosmos. We humans are creatures of these slow pockets. We evolved in the gravity well. Our biology is tuned to the rhythm of a slowed-down clock. We are, in a sense, already time travelers, held back from the true, rapid pace of the universe by the rock beneath our feet. This leads to a strange paradox when we think about space travel. In the previous section, we discussed how moving fast slows down time. Now, we see that leaving gravity speeds up time. These two effects work in opposition. When an astronaut leaves the Earth, they are doing two things simultaneously. They are moving fast, which slows their aging, and they are moving away from Earth's heavy gravity, which accelerates their aging. For the astronauts on the International Space Station, the balance is delicate. They are moving at 28,000 kilometers per hour, a speed that tries to slow their clocks. But they are also floating 400 kilometers up, away from the heaviest pull of the Earth, which tries to speed up their clocks. As it turns out, at that specific altitude and speed, the velocity effect wins, but only by a tiny margin. They age slightly slower than us, but the gain is partially eaten away by the lack of gravity. However, if they were to go higher, if they were to travel to the orbit of the Moon, or beyond, moving slowly, the gravity effect would take over. A human living on the Moon, which has a very weak gravity, would age faster than a human on Earth. The Moon's gravity well is shallow. It does not dig deep enough into the fabric of space-time to slow the clock as much as Earth does. So, a lunar colony would be a place of accelerated aging, a place where the seconds tick by with slightly more urgency than they do on the homeworld. This interplay between speed and gravity creates a complex map of age across the universe. Every planet has its own temporal signature. A civilization living on a massive super-Earth, a planet 10 times the weight of our own, would live in a slower timeline than us. They would gaze out at a universe that seems to move slightly faster than ours. Conversely, a civilization living on a small asteroid would be racing ahead of us, living in the fast lane of low gravity. But the most profound implication of the heavy hand of gravity lies in what it tells us about our connection to the universe. We often feel small and insignificant against the vastness of the stars. Yet, our very presence, our mass, and the mass of our planet are actively shaping the flow of time. We are not just drifting in the current. We are the rocks in the stream that cause the water to divert and slow. The Earth is our shield. It wraps us in a blanket of gravity that keeps the frantic pace of the cosmic clock at bay. It is a protective embrace. By pulling us down, by giving us weight, the Earth is also giving us time. It is a trade-off that defines our existence. We accept the burden of heaviness, the inability to fly, the struggle to stand up, and in exchange, we are granted a slightly longer pause in the moment, a slightly stretched out now. As we venture further into the cosmos, we will leave this protective embrace. We will encounter voids where time races, and we will skirt the edges of black holes where time essentially stops. We will become navigators of these slopes and valleys, learning to chart our course not just through the 3 dimensions of space, but through the undulating topography of time itself. We have now established the 2 great pillars of our journey. We understand the velocity of youth, how speed preserves us, and we understand the heavy hand of gravity, how mass anchors us. But these are distinct, separate concepts in our minds. To truly grasp what it means to age in space, we must bring them together. We must look at what happens when human beings enter this equation. We must move from the theoretical physics of particles and planets to the tangible reality of people. There is a famous story in physics, a parable that has been told for over a century, which perfectly illustrates the strange collision of these 2 forces. It is a story of siblings, separated by the stars, living 2 completely different lives in 2 completely different times. It is the story of the twin paradox, and it is not just a story. It is a prophecy of our future among the stars. We turn now to the human side of the equation. We leave the abstract fabric of space-time and look into the eyes of 2 travelers who, though born together, will not die together. The story of the twins is perhaps the most enduring fable of modern physics. It is a narrative that has been told in classrooms and lecture halls for over a century. serving as a bridge between the cold, hard mathematics of relativity and the warm, relatable human experience of family. It begins with two siblings, identical in every way. They share the same genetic code, the same birthday, and the same timeline. For the first part of their lives, they are synchronized, two clocks ticking in perfect unison. But then, a choice is made that will sever the bond of their shared reality. One twin, let us call him the Traveler, is chosen for a mission to the stars. He boards a vessel capable of reaching speeds that defy our current engineering, accelerating to a substantial fraction of the speed of light. The other twin, the Observer, remains behind on Earth. He stays grounded in the gravity well, living a conventional life, governed by the rising and setting of the sun and the steady, familiar rhythm of the terrestrial calendar. As the Traveler's ship engages its engines and slips away from the solar system, the connection between the two siblings begins to stretch. From the perspective of the brother left on Earth, the ship is a streak of light, moving against the backdrop of the cosmos. If he could peer through a powerful telescope and see into the cabin of the spacecraft, he would witness something unsettling. He would see his brother moving in slow motion. The Traveler raising a cup of coffee to his lips would take minutes. A wave of the hand would seem like a leisurely drift through water. To the brother on Earth, the Traveler has become a statue of living marble, preserved by the immense velocity of his journey. However, inside the ship, the Traveler feels nothing of the sort. To him, the coffee lifts normally. His heart beats at a standard pace. He checks his instruments, reads his books, and sleeps his 8 hours. If he looks back at Earth through his own telescope, the situation becomes confusing. From his vantage point, it is the Earth that is rushing away from him at near light speed. By the laws of relativity, he should see his brother on Earth moving in slow motion. This is the heart of the paradox. If both see the other slowing down, who is actually younger when they meet again? The resolution lies in the journey itself. To return home, the Traveler must do something the brother on Earth never does. He must turn around. He must fire his engines, halt his outward momentum, and accelerate back towards home. In that act of turning, in that violent shift of velocity, the symmetry is broken. The Traveler shifts from one timeline to another. He feels the force of the turn, the pull of the engines, and in that physical reality, the universe renders its verdict. When the ship finally descends back through the atmosphere and the airlock hisses open, the reunion reveals the truth of the cosmos. The brothers stand face to face. The one who stayed on Earth is an old man. His hair is white, his skin etched with the lines of decades, his posture stooped by the weight of years. He has lived a full life, raised children, and watched the seasons turn 50 times. Standing opposite him is the Traveler. He looks almost exactly as he did the day he left. He is still a young man, vibrant and upright. His journey, which felt like a mere 5 years to him, was 50 years to the world he left behind. They touch hands, and in that contact, they bridge two different eras. The Traveler has not just gone to space, he has leaped into the future. He has skipped over the intervening decades, bypassing the slow erosion of time that claimed his brother. For a long time, this story was treated as a thought experiment, a purely mental exercise designed to help students grasp the implications of Einstein's theories. It felt like fantasy, a scenario reserved for the distant future of interstellar empires. But the universe does not require starships to prove its rules. It only requires precision. In the latter half of the 20th century, humanity decided to take this fable out of the chalkboard and into the real world. We decided to prove that the twins were not just a story. In October of 1971, two physicists named Joseph Haffel and Richard Keating set out to perform the most accessible version of this experiment possible. They did not have a starship. They did not have engines that could reach the speed of light. They had something far more mundane: commercial airliners. They reasoned that if the laws of relativity were true, they shouldn't need to travel at cosmic speeds to see the effect. They just needed clocks that were sensitive enough to capture the tiniest slivers of lost time. They selected 4 Gaussian beam atomic clocks. These were not the ticking devices we wear on our wrists, but highly sophisticated instruments that measure time by counting the vibrations of atoms. They are the guardians of the second, precise to a degree that is difficult to comprehend. Losing less than 1 second every few million years, Haffel and Keating purchased tickets on standard commercial flights, essentially booking seats for their time machines. They flew around the world twice. First, they traveled eastward, flying in the direction of the Earth's rotation. Then, they traveled westward, flying against the spin of the planet. It was a strange juxtaposition. While flight attendants served meals and passengers read newspapers, these two scientists sat monitoring devices that were testing the fundamental structure of reality. The logic of their experiment was a beautiful interplay of the two forces we have discussed: speed and gravity. When the planes flew eastward, they were adding their speed to the rotation of the Earth. They were moving faster than a person standing on the ground. According to the velocity of youth, their clocks should slow down. When they flew westward, they were effectively canceling out some of the Earth's rotation speed, moving slower than the person on the ground. Their clocks should speed up, but they also had to account for altitude. Cruising at 10,000 meters, the planes were higher in the gravity well than the clocks left back at the laboratory in Washington, D.C. The weaker gravity meant the clocks on the planes should run faster. It was a complex accounting game, balancing the time gained from altitude against the time lost or gained from speed. When the planes touched down and the physicists returned to the laboratory, the tension was palpable. They compared the traveling clocks with the stationary ones that had remained on the ground. The difference was not visible to the human eye. The clocks did not disagree by hours or minutes. They disagreed by billionths of a second, nanoseconds, but they disagreed. The eastward clocks had lost time, just as the equations predicted. The westward clocks had gained time. The travelers had arrived back in Washington, D.C., slightly out of sync with the rest of humanity. The experiment was a triumph. It proved that the twin paradox was not a paradox at all, but a simple fact of nature. Haffel and Keating had technically aged at a different rate than their colleagues who stayed behind. The difference was negligible, far too small to affect their biology, but it shattered the idea of absolute time forever. Since that groundbreaking journey, we have refined our ability to measure this effect with terrifying precision. In the laboratories of the National Institute of Standards and Technology, physicists have built clocks using aluminum ions that are so sensitive they can detect the warping of time over distances of mere centimeters. In one experiment, researchers placed 2 of these ultra-precise clocks on tables. One clock was then raised just 33 centimeters higher than the other, about the height of a single step on a staircase. That small elevation, that tiny movement away from the center of the Earth, was enough. The higher clock ran faster than the lower clock. The difference was incredibly minute, but it was there. This means that if you stand on a step stool, your head is aging faster than your feet. If you live in a second-story apartment, you are moving through time quicker than your neighbor on the ground floor. We are all drifting through our own personal timelines, separated by the microscopic variations of our height and speed. The tale of two travelers is no longer just a story about the future. It is the reality of the present. Every astronaut who has ever lived on the International Space Station is a living testament to this truth. The Russian cosmonaut Sergei Krivokalev holds the record for the most time spent in orbit, with over 800 days logged in space. Because of the high speeds at which the space station travels, 28,000 kilometers per hour, he has traveled into the future. Calculations show that he is approximately 0.02 seconds younger than he would have been if he had stayed on Earth. It is a ghost of a second, a blink of an eye that went missing, but it belongs to him. He has saved that fraction of time. He has lived longer, in the strictest chronological sense, than the universe intended for a terrestrial human. As we look forward to the era of deep space exploration, the tale of the twins will shift from a curiosity to a profound social challenge. When we send crews to Mars or eventually to the nearby stars, the time gap will widen. A mission to a star system like Alpha Centauri, even with futuristic propulsion, might take decades. If we can achieve speeds of half the speed of light, a crew might return home to find that while they have aged 10 years, the Earth has aged 12 or 13. This disconnect creates a unique form of isolation. The space traveler is not just separated from humanity by distance, they are separated by duration. They become untethered from the collective history of their species. To travel far and fast is to become an exile. The songs, the politics, the cultural shifts, and the daily struggles of Earth will race ahead, leaving the traveler preserved in a bubble of the past. There is a profound loneliness in this realization. We rely on shared time to build connections. We celebrate simultaneous moments. New Year's Eve, the moment of a sunrise, the coordinated ticking of the global clock. To step out of that synchronization is to step out of the human rhythm. The traveler returns as a stranger, a person who remembers a world that no longer exists. They are younger, yes, but they are also out of place, like a note held too long in a melody that has moved on to the next bar. This is the trade-off the universe demands. It offers the gift of preservation, the ability to slow the aging process and stretch the lifespan. But the cost is connection. You cannot stay young and stay with the ones you love. You must choose between the comfort of the shared present and the solitary preservation of the high-speed future. Yet, there is a twist to this narrative. We have focused entirely on the physics of the situation. We have looked at the clock, the atom, and the photon. We have assumed that the human body is merely a passenger, a biological cargo that passively obeys the slowing of time. In the equations of Einstein, the astronaut returns young, healthy, and vibrant, their cells having divided fewer times than their twins. But the human body is not a clock made of cesium or aluminum. It is a fragile, wet, biological machine evolved to live in the protective embrace of Earth's atmosphere and magnetic field. While physics is busy preserving the astronaut's timeline, the environment of space is actively attacking their biology. The paradox of the twins assumes a sterile, perfect journey, where the only variable is speed. It does not account for the harsh reality of cosmic radiation, the withering effects of microgravity, or the immense stress of isolation. Physics tells us that the space traveler should age slower, but biology often has a different opinion. While the calendar might say the astronaut is younger, their arteries, their DNA, and their bones might tell a story of accelerated decay. We must now turn away from the clean elegance of relativity and face the messy, complex reality of human physiology. We must ask, does the body actually enjoy the extra time the universe grants it? Or does the rigor of the journey destroy the gift before it can be enjoyed? The tale of the two travelers is not just about time dilation. It is about the conflict between the laws of physics, which want to keep us young, and the laws of biology, which seem determined to tear us apart in the void. We enter now the biological paradox of spaceflight, where the theoretical fountain of youth meets the harsh radiation of the stars. There is a profound irony waiting for us in the silence of the void. We have spent much of our journey exploring the elegant mathematics of relativity, a set of cosmic laws that promise a form of preservation. We have learned that speed is a shield, a mechanism that slows the ticking of the clock and stretches the duration of a human life. If we view the human being purely as a physical object, a collection of atoms moving through space-time, then the verdict is clear. The astronaut returns younger than the twin they left behind. But a human being is not merely a collection of atoms. We are not blocks of quartz or beams of light. We are biological entities, soft, wet, and fragile, evolved over millions of years to exist in a very specific, very sheltered environment. We are creatures of the gravity well. Our bones, our hearts, our eyes, and the complex chemistry of our cells were all sculpted by the constant, unyielding pull of the Earth and the protective embrace of its atmosphere. This brings us to the biological paradox of spaceflight. While the laws of physics are working to keep the astronaut young, the environment of space is working tirelessly to age them. It is a silent battle between the geometry of the universe, which offers time, and the biology of the body, which succumbs to stress. When we look at the reality of long-term space travel, we find that the chronometer might say one thing, but the mirror says something entirely different. The first enemy of youth in space is the very thing that makes spaceflight seem so dreamlike: weightlessness. On Earth, gravity is the constant sculptor of our bodies. Every time you stand up, your muscles must fire to hold your skeleton together. Every time you take a step, your bones feel the impact, a microscopic shock that tells the body to strengthen the structure. Your heart has to pump with vigor to push blood up against the pull of the planet to reach your brain. We are constantly working, constantly resisting, even when we feel we are at rest. In the free fall of orbit, this resistance vanishes. The astronaut floats. The effort required to move becomes negligible. You can push a heavy equipment rack with a single finger. You can drift from one end of a module to the other with a gentle kick. It feels like absolute freedom, a liberation from the heavy burden of existence. But the body interprets this freedom as a signal to shut down. Without the constant stress of gravity, the human body assumes it no longer needs its heavy infrastructure. It begins a process of ruthless efficiency, dismantling what it perceives as unnecessary tissue. This is not a slow decline. It is a rapid acceleration of decay that mimics the most aggressive forms of aging we see on Earth. Consider the skeleton. On Earth, our bones are in a constant state of renewal, breaking down old tissue and building new layers to handle the weight we carry. In space, the building stops, but the breaking down accelerates. And Astronaut can lose 1 to 2% of their bone mass for every single month they spend in zero gravity. This is a rate of loss that would be considered catastrophic in an elderly patient suffering from osteoporosis. The calcium that is stripped from the bones does not just vanish. It floods the bloodstream, overloading the kidneys and creating a high risk of painful stones. The astronaut is physically dissolving, their internal structure becoming brittle and porous. The muscles follow a similar trajectory. The heart, which is a muscle, finds that it no longer needs to work as hard to move blood around the body. It grows lazy. Over the course of a long mission, the heart actually shrinks, losing mass and changing shape, becoming more spherical. The leg muscles, which are the pillars of our terrestrial life, begin to atrophy within days. Without rigorous, punishing daily exercise, hours spent strapped to treadmills and resistance machines, an astronaut would return to Earth unable to stand, their legs having wasted away to match the demands of a weightless life. Then there is the issue of fluids. On Earth, gravity pulls the fluids of the body downward. We evolved with a circulatory system designed to pump against this pull, ensuring the head gets enough blood. In space, with gravity removed, the fluids rush upward. The legs become thin as the blood leaves them, while the head becomes engorged. Astronauts often speak of a permanent feeling of congestion, a stuffed nose, and a puffy, swollen face. This is not just a cosmetic issue. The increased pressure inside the skull presses against the backs of the eyes, flattening the eyeballs and damaging the optic nerves. It is a condition known as spaceflight-associated neuroocular syndrome, and it means that many astronauts return home with their vision permanently altered, their eyes having aged decades in the span of months. But perhaps the most insidious threat to the youth of the traveler comes from the invisible storm that permeates the cosmos: radiation. Here on the surface of our planet, we are shielded. The Earth has a molten iron core that generates a massive magnetic field, a bubble that deflects the harsh solar wind and the high-energy cosmic rays that rain down from deep space. We are also wrapped in a thick blanket of atmosphere that absorbs ultraviolet light and X-rays. We live in a sanctuary. To leave the Earth is to step out of that sanctuary and into a firing line. The hull of a spacecraft, usually made of thin aluminum, offers very little protection against the most energetic particles. Galactic cosmic rays, shards of atoms blasted out by exploding stars, can pass through the walls of the ship and through the body of the astronaut as if they were made of smoke. When these particles strike human tissue, they act like microscopic bullets. They tear through the delicate machinery of the cells. They shatter the molecular bonds of the genetic code. The body is resilient. It has repair mechanisms designed to fix small breaks in the double helix of our biological blueprints. But in space, the damage is constant and cumulative. This creates a state of oxidative stress, a condition where the body is overwhelmed by the need to repair itself. This is the very definition of biological aging at a cellular level. It is the accumulation of errors, the slow degradation of the instructions that keep us alive. So, we have a strange duality. The high speed of the ship is slowing down the vibration of the atoms, preserving the astronaut in time. But the radiation is smashing those same atoms, accelerating the decay of the cells. The physicist says the traveler is young. The doctor says the traveler is old. To understand which force wins this tug of war, we do not need to rely on theory. We have witnessed this paradox in a real-world experiment that perfectly mirrors the story of the twins we discussed earlier. In the 21st century, the United States Space Agency conducted a landmark study involving two identical twin brothers, Scott Kelly and Mark Kelly. Both men were astronauts, but for this experiment, their paths diverged. Mark Kelly, the observer, remained on Earth, living a normal life in the gravity well, subject to the standard flow of time and the standard protection of the atmosphere. Scott Kelly, the traveler, launched to the International Space Station, where he lived for nearly a year. He orbited the planet thousands of times, moving at 28,000 kilometers per hour, floating in microgravity and exposed to the higher radiation environment of low Earth orbit. For a year, the twins were the perfect test subjects. Scientists monitored every aspect of their biology, from the bacteria in their digestive systems to the length of their chromosomes. They wanted to see if the twin paradox of physics had a biological counterpart. The results were fascinating and contradictory. One of the key markers of aging is the length of telomeres. Telomeres are the protective caps at the ends of our chromosomes, often compared to the plastic tips on the ends of shoelaces. Every time a cell divides, the telomeres get a little shorter. When they become too short, the cell can no longer divide and dies. Short telomeres are a hallmark of old age. When Scott Kelly went to space, something unexpected happened. His telomeres did not shorten. In fact, they grew longer. While he was in orbit, his cells seemed to revert to a more youthful state. It was as if the stress of the environment had triggered a desperate survival mechanism, a temporary fountain of youth that lengthened his cellular fuse. For a brief moment, it seemed that space might indeed be a place where aging stops. But the illusion was shattered the moment he returned to Earth. Within 48 hours of landing, the lengthening effect vanished. His telomeres shrank rapidly, losing all the ground they had gained and more. The tax of the journey was collected the moment he re-entered the gravity well. Furthermore, the study found that he had suffered significant damage to his genetic code that did not fully repair itself even months later. His immune system was on high alert, and his cognitive speed, the sharpness of his mind, had declined slightly compared to his brother. So, who was the younger twin? Chronologically, according to the laws of general and special relativity, Scott Kelly had traveled into the future. He was younger than Mark by a few milliseconds, but biologically, the stress of the year in space had aged him. His arteries were stiffer, his vision was changed, and his cellular machinery carried the scars of cosmic radiation. He had gained time, but he had lost vitality. This is the biological paradox. We can use speed to outrun the clock, but we cannot outrun our own biology. We are soft machines built for a quiet, heavy life on a garden world. When we throw ourselves into the void to chase the horizon of immortality, we are subjecting ourselves to an environment that is fundamentally hostile to our existence. This realization casts a shadow over our dreams of interstellar travel. It suggests that even if we build ships that can reach near-light speeds, ships that allow a crew to travel to the Andromeda Galaxy and return in what feels like a few years, the crew that steps off that ship might be broken ruins of human beings. They might be chronologically young, having aged only a handful of years, but their bodies might be ravaged by the cumulative dose of radiation and the wasting effects of zero gravity. They would be young in years, but ancient in constitution. It forces us to ask, what is the value of a saved second if the body spending it is broken? If we are to become a true spacefaring species, We cannot rely on physics alone. We will need to master biology. We will need to learn how to shield our fragile genetic code from the sleet of subatomic particles. We will need to create artificial gravity, spinning our ships to mimic the heavy embrace of the Earth, tricking our bones into thinking they are still at home. We will need to merge the mechanical preservation of relativity with a new kind of biological preservation. Until then, space travel remains a trade. It is a negotiation with the universe where we exchange our health for our horizon. The astronaut is a pioneer, not just of new worlds, but of a new kind of human existence, one where the arrow of time and the arrow of biology no longer point in the same direction. As we look deeper into the cosmos, beyond the planets and the stars, we find places where this conflict becomes even more extreme. We have looked at the gentle time dilation of Earth and the moderate time dilation of a speeding rocket. But there are places in the dark where the warping of time is absolute. There are chasms in the universe where gravity is so strong that it does not just slow the clock, it threatens to stop it altogether. In these regions, the biological paradox becomes meaningless because biology itself ceases to exist. We are approaching the ultimate frontier of time. We are turning our gaze toward the dark hearts of the galaxies, to the event horizons of black holes. Here, at the edge of the abyss, the concept of aging requires a new definition entirely. We prepare now to enter the region of frozen time, where the seconds stretch out into eternity and the universe holds its breath forever. We have traveled from the familiar ticking of clocks on Earth to the high-speed corridors of interstellar space, and through the biological frailty of the human body suspended in the void. We have seen how speed acts as a preservative and how the gentle gravity of a planet acts as an anchor. But there is one final destination on our journey, a place where these forces are taken to their absolute, terrifying, logical conclusion. It is a place where the concept of aging does not just slow down or shift, it fundamentally breaks. We are turning our gaze toward the dark, silent hearts of the galaxies, to the objects that astronomers once called frozen stars, but which we now know as black holes. Here, at the edge of the event horizon, the question of why we age slower in space finds its ultimate answer. In the vicinity of a black hole, gravity is not merely a force that holds a solar system together. It is a tyrant that dominates the structure of reality. The mass compressed into these singularities is so dense and the gravity well so deep that it drags the fabric of space-time down into a bottomless pit. If the Earth is a gentle dimple in the sheet of the universe, a black hole is a puncture. To understand the fate of time in such a place, we must imagine a final, hypothetical mission. We send a solitary traveler, a brave volunteer, to descend toward the event horizon of a supermassive black hole. We, the observers, remain safely parked in a starship far away, watching through our telescopes. This scenario reveals the most profound divergence of reality allowed by the laws of physics. As the traveler approaches the black hole, the gravity begins to claw at the seconds of their life. We have already established that being in a gravity well slows time. But this is not the subtle slowing measured by atomic clocks on Earth. This is a dramatic, visceral breaking of existence. From our safe vantage point, we watch the traveler's ship descend. At first, they accelerate, pulled in by the inescapable attraction of the void. But as they get closer to the horizon, the point of no return, something strange begins to happen. We do not see them speed up. We see them slow down. The light coming from their ship has to climb out of that deep gravitational pit to reach our eyes. As it climbs, it loses energy. In the physics of light, losing energy means the wavelength gets longer, and the color shifts toward the red end of the spectrum. This is known as gravitational redshift. The image of the traveler becomes redder and dimmer, fading like a dying ember. But more importantly, the image becomes sluggish. If the traveler were to wave to us, we would see their arm lift, but it would take an eternity to lower. If they were wearing a watch with a glowing face, the second hand would begin to tick slower and slower. Tick, and we would wait, and wait. Tock. The gap between the seconds would stretch from moments to minutes, then to hours, then to years. From our perspective, the traveler never actually falls in. As they reach the very edge of the event horizon, time for them, relative to us, grinds to a complete halt. They become frozen. The image of their ship is plastered against the black sphere, a faint, red, motionless ghost. They are trapped in a state of eternal suspension, preserved forever at the last moment of their visible existence. This is why early physicists used the term frozen stars. To the outside universe, nothing ever truly falls into a black hole. It just gets stuck on the edge of time, caught like a fly in amber, fading slowly into invisibility over eons, but never completing the fall. This is the ultimate preservation. If you could hover just a millimeter above the event horizon without being destroyed, you would be virtually immortal relative to the rest of the universe. A minute spent there would see empires rise and fall back on Earth. A polite conversation over tea would outlast the entire remaining lifespan of the sun. You would be disconnected from the flow of history, a statue in a museum, while the world outside rushes through its entire exhibit. But this is only half the story. The paradox of relativity is that there is no single truth. While we see the traveler freeze and fade, the traveler experiences something entirely different. From inside the ship, the traveler feels no braking force. They do not feel themselves slowing down. Their watch continues to tick at 1 second per second. Their heart beats at its normal rhythm. They look out the window and see the event horizon approaching, but they do not stop. They cross the line. There is no signpost, no barrier, no bump in the road. They simply glide across the threshold from which light cannot escape, falling toward the singularity in the center. However, if the traveler were to look back over their shoulder, back toward the universe they are leaving behind, they would witness a sight that defies comprehension. Because they are moving into a region of such intense slow time, the universe outside appears to speed up. If they could see clearly, they would see the stars of the galaxy circling like the blades of a fan. They would see the evolution of the cosmos playing out in fast forward. The entire future of the universe might flash by in the few moments before they reach the center. They have traveled to the end of time. They have reached a place where the concepts of before and after are twisted until they break. Inside the black hole, space and time actually swap roles. The radial direction, the path downward toward the center, becomes time. You can no more stop falling toward the center than you can stop tomorrow from arriving. The singularity is not a place in space. It is a moment in your future. It is a date on the calendar that you cannot avoid. This is the terrifying beauty of the black hole. It is a machine that processes time. It consumes the present and hoards it. It is the edge of the map, and yet, in this extreme, we find the echo of the same principle that governs the astronaut on the space station or the commuter on the highway. It is all the same mechanism, just dialed up to infinity. The universe allows us to trade our location for our duration. We began this documentary by asking why we age slower in space. The answer, we now realize, is that aging is not a universal constant. It is a local experience. It is a transaction between you and the universe. When we stay on Earth, we are making a specific deal. We accept a short, fast life in exchange for the warmth of the sun and the company of our fellow humans. We agree to all march to the beat of the same drum, synchronized by the gravity of our planet. But space offers a different deal. It offers us the chance to step out of that rhythm. It offers us the chance to hoard our seconds, to stretch our lives across a wider canvas of history. The faster we move, and the deeper we dive into the gravity wells of the cosmos, the more we detach ourselves from the timeline of our birth. We are, in the truest sense, creatures of time. We are made of memories and moments. The realization that these moments are elastic, that they can be stretched, compressed, and saved, changes our relationship with existence. It means that we are not trapped in a river that flows at one speed. We are swimmers who have learned that if we swim fast enough or dive deep enough, we can change the current. For now, our ability to use this knowledge is limited. We can shave off fractions of a second on the International Space Station. We can dream of ships that will save us years on a journey to the stars. We are still dipping our toes into the ocean of time dilation. But the physics is real. The door is open. As we look to the future, we can imagine a civilization that uses this knowledge not just for exploration but for survival. We might one day build arcs that circle black holes, waiting out a cosmic catastrophe, skipping over dangerous millennia to emerge in a quieter era. We might send emissaries to the stars who return as living history books, young witnesses to an ancient past. We might become a species that does not live in a single now, but spreads its existence across the eons, a tapestry of humanity woven through time as well as space. But there is a gentle warning in this grandeur. The preservation of youth in space comes at the cost of separation. To stay young is to be left behind, or rather, to leave everyone else behind. The astronaut who returns young has missed the life that happened while they were away. They have missed the birthdays, the gradual aging of their parents, the changing of the seasons, and the slow, quiet evolution of culture. They have saved their own time, but they have spent their connection to home. Perhaps this is why we cherish the illusion of universal time on Earth. It is the glue that holds us together. It allows us to meet, to love, and to build together. The fact that we all age at roughly the same rate is not a curse. It is the condition that makes community possible. We move through the dark together, hand in hand, aging in unison. So, the next time you look up at the night sky, at the wandering planets and the distant glittering stars, remember that they are not just places. They are different times. They are islands of now, separated by the vast ocean of the past. And remember that while the universe offers us the keys to immortality through speed and gravity, the most precious time is the time we share. We age slower in space because space is a lonely place where the universe holds onto its moments a little tighter. But here, on this spinning blue rock, we spend our moments freely. We let them slip through our fingers like sand, not because we are careless, but because we are together. And in the end, that shared journey through time, fleeting as it may be, is the only journey that truly matters.